Another exam paper, that was the exam from exactly 2 years ago, May 2015. And there are a few exercises in this exam that actually are different from what we did last week. Namely, that year I asked some questions on statistics, so we're going to do one question on statistics. There was one sub-question on using Chebychev inequality, also that was not covered last time. And there is also some change of variables when we have two random variables and we change them into two other random variables, right? So, so that's why I want to cover this exam as well, so that I can give you a quite broad overview of the type of questions you may expect or you may get. Okay, so the first question is the following. We have a random variable x, and we say it's continuous. And we have a certain probability density function, and we ask first compute the cumulative distribution function of x. Right? That's the first one. The second sub-question is compute expectation of x and variance of x. Right? So this is really, really classical questions. Again, same as what we had last week, just to make sure that actually on those two sub-questions you should get maximum marks. Right? Okay, so what does that mean? So we have a continuous random variable whose PDF is given by -2, 1 minus x for x between 0 and 1, and otherwise it's 0. Right, so first sub-questions, we say compute the cumulative distribution function of x, right? So what does that mean? That's the probability that x is smaller or equal to x, essentially. That's what it means. Right, so what can we do? We can apply directly the definition, which is the integral between minus infinity and x, right, this argument here, of this probability density function. Okay, and so what we see here is actually this PDF is non-zero between 0 and 1. So what does that mean? That means that actually if x is smaller or equal to 0, right, the integral between minus infinity and x will be 0, right? Good. If x is between 0 and 1, we have the integral between 0 and x of 2, 1 minus x dx. Right, so this is 2x minus x squared. And if x is larger or equal to 1, what we should have? We should have the CDF is equal to 1, right? And you can see when x is equal to 1, actually here the boundaries that you have, indeed, the CDF is equal to 1. Okay, so this is really, really fundamental. Second one, expectation of x. Again, what is the definition of the expectation of x when you have continuous random variable, integral between minus infinity and plus infinity of x multiplied by the PDF of x, right? So in this case, the boundaries is 0 between 0 and 1, because otherwise we have 0. So it's 0 to 1 of 2x, 1 minus x dx. Right, so you can compute this, and this gives you 1/3. Okay, so I think all of your classmates did well there. Right, this should be quite easy for all of you. Variance of x, again, same trick as what we did last week. What is the variance of x? Is the expectation of x squared minus the square of the expectation. This one we know already. That's going to be 1/3 square. What is missing is expectation of x squared. So that's going to be the integral between 0 and 1 of 2x squared 1 minus x dx. Right? So this is the PDF, and this is the x squared. Okay, so you can compute this. There's no difficulties here in computing the integral. This is 1/6. So you get 1/6 minus 1/9, and you get 1/18. It's okay for all of you? Yeah? That should be, right? Okay, third sub-question was about computing a moment generating function, right, of this random variable x, and then use it to find the expectation and the variance of this random variable. Right? We have already computed the expectation and the variance, but there is another way of doing it, is by first computing this moment generating function, and from there using some relationship that we have used in the lectures, and we played with already last time. So what is the moment generating function of x? Right, is expectation of etx, right? And so here, what would it be? Is the integral between minus infinity and plus infinity of etx multiplied by the PDF of x. Right, so you can write your whole thing. Essentially here will be between 0 and 1, again, given your boundaries of etx to 1 minus x dx. And you can compute this integral. You can do integration by parts, typically because you have this expectation here, exponentially here, and x there. And you can compute this integral by part. I will not do this here. You can do this at home. What you get is 2et minus 2 minus 2t over t squared. Right? There's no major difficulties here. It's just direct integration by parts. Okay, so this is all right. Now what you see in this function is that you have a t squared, the denominator. So that means that if you evaluate this function at t equal to 0, you're going to have 1 over 0 here. Right? And the numerator here, what do you have if you evaluate at t equal to 0? You're going to have a 2 here, minus 2. That's 2 minus 2, that will be 0, minus 2 times 0, that will be 0. So you're going to have a 0 over 0. Okay, so interestingly, your classmate 2 years ago, many of you, or many of your classmates, had really difficulties with this. And I don't know why, because this is about computing some form of limits using some L'Hopital rules. So I do hope that you all know L'Hopital rule now, right? Because this creates some issues 2 years ago. So why do we have to compute this limit? Because in the question we say, well, compute the expectation using this moment generating function. Right? So what is the expectation of x? The expectation of x is obtained by taking the derivative of that moment generating function and evaluate this at t equal to 0. Okay? So what is this derivative of this moment generating function evaluated at t equal to 0? This is the limit when t goes to 0 of mx of t minus mx of 0 divided by t minus 0. This is just the definition of a derivative. Right? I'm writing it this way, but you could take the derivative of this function here and evaluate it at t equal to 0. It's exactly the same thing. Right? Now, when you compute this, mx of 0, right, the moment generating function of 0, if you plug 0 into this, you get 0 over 0. Right? So what you have to do is to take the limit when t goes to 0 of the derivative of the numerator divided by the derivative of the denominator. Right? So you have 2et minus 2 divided by 2t. What do we get here? It's going to be 2 minus 2, that's 0 over 0. 0 over 0 again. What do? We do it again. Right? So that's limit when t goes to 0 of 2et divided by 2. And so this gives you 1. Okay, so this term here is equal to 1. Right? So now you can compute this limit again. You have this moment generating function is here, minus 1 divided by t. And you can compute the value of this derivative of this moment generating function evaluated at 0. But you're going to have, again, to apply L'Hopital rule. Right? And you're going to have to do it 2 or 3 times. Right? So the issue here is that I had many students, they say, well, we take the derivative, we evaluate it at 0, and then actually they cannot do it. Right? So it's just computing a limit, right? This is supposed to be A level, actually. So if you do this, you get, obviously, you get the same answer as what we had here. You should get 1/3. Okay, so give a try at home. Make sure that you can compute, again, this limit by applying L'Hopital, exactly as we did it here, but you're going to have to do it once again here. Okay? Okay, so for the variance of x, well, we know already the variance of x is expectation of x squared minus the square of the expectation. Expectation of x squared, how can we get this? Well, by taking the second order derivative of x, of the moment generating function of x, evaluated at 0. Okay, so same thing here. Once you have the derivative of that function, you can take again the second order derivative, and take a limit when t equal to 0. And you're going to apply L'Hopital again. Okay, so it's a matter of actually knowing L'Hopital rules and applying it. Okay, so here you do this and you get, again, same answer as what we had here, so 1/18. Right? So is it all clear, this, for all of you? Right? Because this is really, really fundamental. It has nothing to do with probability, but you have to be able to compute, obviously, a limit, right? When you have a 0/0, infinity/infinity. Okay? Okay, good. Any questions here? It's okay? So fourth sub-question is about Chebychev inequality. So this is a bit different. So we didn't play with this last week. So what do we say? We say make use of Chebychev inequality to determine a bound on this probability and then compute the exact value of this probability, right? So this Chebychev inequality, remember, is an inequality that helps you to bound some form of probability without even knowing the distribution of the random variables, right? That's the power of Chebychev. So even if you don't know the PDF of X, you could still provide some bounds on this probability, right? So what we have seen in the lectures is that we've seen the Chebychev inequality that was saying the deviation of x versus b is this probability. So it's very similar to what we have there, except that b is equal to 1/3 and a is equal to 1/4. This is always bounded by the expectation of x minus b squared divided by a squared. Right? So in our case, what do we have? We have the probability of x minus 1/3 larger or equal to 1/4, and this is smaller or equal to expectation of x minus 1/3 squared divided by 1/16. That's what it means. So what is this? We have done this already before, because 1/3 is the expectation of x. Okay, so this quantity here is nothing else than the variance of x. So this is equal to 16 multiplied by the variance of x. And the variance of x is 1/18. So this is equal to 16/18, or 8/9. Okay, so this is a bound on the on this error probability. And this would actually hold for any distribution here. Right? Okay? Now, what we can do, and this is the second part of the question, we say compute the exact value of this probability. In this case, we know exactly the probability density function, so we can actually compute this probability more accurately. Right? So how can we do this? We can write this again here. And how can I compute this? I can simply go through its complement and say this is the probability that x 1/3 is smaller or equal to 1/4, and then I can expand this. This is the probability that x minus 1/3 is larger or equal to 1/4. And you can bring this over each side of the inequality. And so this is 1/12 and 7/12. Okay, so here I have essentially expanded this relationship, and now I have a function. This is a function of a probability right? And what does that mean? That means actually I have 1 over 12 and 7 over 12. And I'm looking at, I have a certain curve like this, and I'm looking at this area here, right? So what is this area? Well, you can compute this by saying this area will be the cumulative distribution function of x evaluated at 7 over 12 minus, so that's going to be this area here, right? That's this quantity, minus this quantity here, right? This is f of x evaluated at 1 over 12, right? So the answer is 1 minus f of x 7 over 12 plus f of x at 1 over 12. And this cumulative distribution function, we know it already. It was evaluated here, right? So you can plug those two quantities here, those two values into the CDF, and you get 1 over 3, right? So if you compare the two, this is 1 over 3, this is 8 over 9. There is a gap between the two, right? And this is due to the fact that, well, in the second case, we know exactly the distribution of x, so we can compute it accurately, while with Chebychev, it's just a bound, right? But that bound would hold for any distribution, okay? Okay, so I think here, for most of your classmates, it was fine, except for the third sub-questions, where I had lots of issues with this computing this limit. Okay, so, yes?
You also got variance of x bar equal to 0, so you've got 0, 0.
The variance of x bar is not equal to 0. Well, in the limit, right? But so that means actually the variance of x bar is tending towards smaller and smaller because actually your estimator becomes more and more accurate. That's what it means, right? But the distribution will look like kind of Gaussian, but you're going to have a variance that will decrease. That's what it means. Okay? So this is a little trick to try to approximate essentially a certain distribution using the central limit theorem. Yes? If you write x?
Instead of x bar in the x-band.
Well, x bar here is really your random, sample mean, right? Your x and your x bar is not the same thing. Right? You understand the difference, right? All your x bar is actually an arithmetic sum, or arithmetic mean of those x1 to xn, right? And each of those x1 to xn actually are distributed using a certain distribution. This is the distribution of x. Okay, so strictly speaking, it's not really accurate. Okay, so this was for the first question. The second question was about something quite similar to what we did last week, in the sense that we have we have two random variables, and in this case we say they're continuous. Last week we had something that actually they were discrete, right? This time it's continuous, and we have a joint probability distribution function, and we asked to compute a certain number of things, right? So what is this joint PDF of x and y? Is two exponential of minus x plus y, and I have here something that you have to pay attention to, is the domain. Right? So I have a domain here that is not rectangular. Right? I have a domain where I'm saying y is larger than x. Okay? So be careful about this. So first sub-question is compute expectation of x. Okay, so one way to do this is first to compute the marginal of x. Right? We have a joint probability density function. Let's compute the marginal of x. So what would be the marginal of x? That would be the integral of the joint probability density function xy over all y, for y from minus infinity to plus infinity, right? So what can I write here? My joint PDF is e minus x plus y dy. What is the boundary here? Any suggestion? Sorry? That's right. Right? So I'm integrating here this joint PDF with respect to y, and y goes from x to infinity. Okay? Not from 0 to infinity. Right? I'm looking at the marginal of x, so this will be a function of x. The boundary here can be a function of x. Okay? So be careful. It's easier when you have rectangular domain because you don't have to look at those boundaries, but here you don't have a rectangular domain. Okay, so this is essentially two, you can compute this and you get 2 exponential minus 2x, and this is for x positive, and otherwise you essentially get 0. Okay, so what you see here, what is this? It should give you a hint. That's right. So x is exponentially distributed with parameter lambda equal to 2. Right? So remember that the expectation of x when you have a exponential distribution is 1 over lambda, right? So this is 1 over 2. Okay? The exponential distribution is relatively easy to play with and to remember, right? So that's why you have lots of exponential distribution in this course, and actually it's very useful. In communication is used extensively. Okay, second sub-question is make a change of variables. So we have 2 new random variables, u, that is y minus x, and v, that is equal to x, and compute a joint probability density function of u and v. Right, so that means that x is equal to v and y is equal to u plus v. Right, so what is this joint PDF of u, v? Well, remember you have to compute the determinant of a Jacobian multiplied by the joint probability density function of x, y. Right, so what you have to compute here is first the Jacobian. So what is my g? Is the derivative of x respect to u, derivative of x respect to v, derivative of y respect to u, derivative of y with respect to v. And so what is this? I'm taking my relationship here, dx du, that's 0, dx dv, that's equal to 1, dy du is equal to 1, dy dv is equal to 1. Okay, so what is the absolute value of determinant of this Jacobian? 1. So what I have left there is now the joint PDF of uv will be 1 multiplied by the joint PDF of x, y, and I can replace the value of x and y by now v and u plus uv. So I have 2, let me write here, 2 exponential of minus x plus y here. Right? X is equal to v, and y here will be equal to u plus v. So I'm going to have e minus u plus 2v. Okay? Now, but we have a domain here, right? We have this domain here. Let's say x should be smaller than y. So if I'm writing this, my domain was x smaller than y, larger than 0, smaller than infinity. X now is v, so I can write v, and y is u plus v. So I need to satisfy this. Right? So that's sufficient to have v will be positive, and to have this relationship satisfied, I need to have u needs to be positive. Okay? And otherwise, if I don't have this, then the joint PDF is equal to 0. So here I have 0 otherwise. Okay? All good? Now, what do you see here again? If I'm writing this differently, this is e minus u multiplied by 2e minus 2v. Does that give you some hint? Yes. That's right. The first one here is an exponential random variable. U is exponentially distributed with parameter lambda equal to 1. Right? So I can say U will be exponentially distributed with parameter lambda equal to 1. V will be exponentially distributed with parameter lambda equal to 2. Right? That's not in the question, but if you notice this, things goes much faster. Right? Because the next sub-question is compute the marginal of U and V. Right? That's the third sub-question, or C if you like. That was A, this is B, and this is C. So what is the marginal of U and V? Well, we have them here. U is exponentially distributed. This will be the marginal of U. V is exponentially distributed. This is the marginal of V. Okay? So you can say that U will be E of U for U positive and 0 otherwise. And V will be 2E minus 2V for V positive and 0 otherwise. This is the marginal of U and V. Yes? If you ignore these two here. Well, this is the distribution, the PDF, right? So mathematically it doesn't change, but actually if you want to separate them neatly, yeah, you put the U on this side so that you can have V is indeed exponentially distributed. Now, if you don't do this, if you don't notice exponentially distributed, you can still do, apply the definition. If you want to have the marginal of U and the marginal of V, you can simply take the integral of the joint PDF over, the other random variables, right? So you can do this. It just would give you exactly the same results, but it would take more time. Right? So what about next one? U and V independent. Right? We know it already. You can see here that those two are the two marginal. If you multiply them together, you essentially get the joint PDF. So U and V indeed, U and V are independent. Why? Because the joint PDF of UV is equal to the product of the marginal of U and the marginal of V for all U, all V over the whole domain. Okay? E. Compute the conditional probability density function of U given V. What is this? That's right. They're independent, right? So the conditional probability is equal simply to the marginal of U here. So this is equal to the marginal of U, right? F. Compute the conditional expectation of U given V. Expectation of U given V. Again. What is it? They're independent, so expectation of U, right? What is the expectation of U? It's exponentially distributed with parameter lambda equal to 1. So it's 1 over 1. That's equal to 1, right? So it's very quick. G. Make use of F and show that and compute the conditional expectation of Y given X by using this relationship. So I know that 1 is equal to expectation of U, conditional expectation of U given V, right? And what I'm looking at is expectation of Y given X. What is U? U, you remember, is Y minus X, right? So I can say this is expectation of Y minus X given V, and V is X. This is expectation of Y given X minus expectation of X given X. What is this? X, right. What does that mean? You know X, and you're looking at the expectation of X, but you know X already, right? So it can only be X. You know everything, right? So this is X. So this expectation of Y given X is 1 plus X, right? And again, I stressed this last time, but again, what you see is that your conditional expectation here is still a random variable, right? Here is still a function of X, right? It's a random variable, right? So you can take an expectation of that conditional expectation. And this is what you can do in the last one. Making use of G, compute the expectation of Y. What can I do? Well, expectation of Y will be equal to the expectation of the conditional expectation of Y given X. Right? We have done this. We have done this. We did this last week. And we did this many times during the lectures. Right? So this is expectation of 1 plus X. An expectation of X, we have done this already. This is 1 plus expectation of X. This is 1 over 2. So this is 3 over 2. Okay? So what you see in this exercise here, the second one, is that actually you don't have to do many calculations. If you notice things go pretty fast, right? And especially the use of independence simplifies a lot of things typically, right? Your conditional PDF or your conditional expectation, all those things simplify significantly, right? If you don't notice the independent, then things get very messy, obviously. Okay? All good? Okay, so that was the exam of 2 years ago, essentially. It was okay. I mean, usually the marks are very widespread, so you can see really students who really grasp everything, and those who actually have some difficulties in some questions. But overall, it was okay. Okay, so I think that's it for today. You may have a third session next week with Dan on probably exam of last year, 2016. Okay. In any case, if you have other questions, do not hesitate to either send me an email last minute. Right? I know some of you like doing this. But otherwise, I wish you good luck for your exams.